I assigned the variable u. And in fact, the only reason it's called u is because I asked everybody in the class to make up a letter for it. And somebody, you? No? Who was it? Good. There! That's him! Okay? He said that this shall be called u. So 2 pi over lambda times sine theta, the reason we call it u because he wants it. Okay?
Call it something that we never use. Nobody uses. No, omega.
What? You could use a different variable, but the grader would appreciate it if the solution were familiar. So we started out with this variable u, and actually the grader will wonder, I never saw this convention for u, and they'll start to wonder what the hell is going on. But everybody knows how to do the derivation.
Okay. Sorry, this the last equation. That's sine theta. That's sine u a, right?
That's setting this equal to pi. Okay. And that's the condition for here.
So that's sine.
If this equal to 2 pi, that's the condition for here.
So that's sine. That's pi sine theta. Pi
sine theta.
Oh.
Times a over lambda. Yes. That takes 0 over pi. Do people want to put some numbers in this one for a moment? Would that make you feel a little more comfortable?
Yeah.
I'm seeing a few vigorous. Some people want to move on. Okay, we'll move on. See what the next one says. Okay. Aha!
Yeah.
A single split.
That's much better.
So the person who didn't want to see numbers in it knew that this is the next problem, which is why. Which is why I do this diagram. Okay. This is a single slit whose width is A. The distance to the screen is still 5 meters. And A, oh shoot, that's a funny notation in the figure. The thing I call A is the 0.15 millimeters. Does everybody see that?
Yeah.
Okay.
Should we change it?
Oh, we're making the width A?
I always call my slit width A and my separation between the slits little d. And my distance to the screen capital D. It's just what I do. Every time we change textbooks, they change that, but I remain the same. Okay. Okay. Everybody agreed with that?
Yep.
Now, part A, make a sketch of the diffraction pattern and put your sketch on the figure. This is our sketch. Is everybody happy with it? Okay. Now, move down so we can see what part B says. What is the width of the central peak in the diffraction pattern? How would I find out the width of the central peak? Because the only thing I'm going to be able to get are y values. This is y equals 0, right? So what would I like to know the y of to get the width of the central peak?
Lambda.
Suppose I found the y of this.
Double it.
Then I could double it. Everyone agreed? So if I find the y to here, I take that y and double it, and I've got the width of the central peak. Everyone agreed? So my two equations are going to be A sine theta is lambda, and tan theta is y over d. So, they gave me A. Did they give me a wavelength?
Yeah.
Can you scroll up to see the wavelength? Okay, 0.633 micrometers. Okay? So in that case, Do you want to do the whole thing in millimeters or the whole thing in micrometers? Let's do it all in micrometers. So we'll move this 3 over. So 150 micrometers times sine theta equals 0.633 micrometers. That's this one. Everyone agreed? So that leads to what for theta? What is theta? .24 degrees. Now what do I do with that theta? I put it in the other equation.
Meters to length.
And then I say tan of 0.24 is equal to y over,
500.
might as well do this in centimeters, right? 500 centimeters. So what's y?
2.1.
How much?
2.1.
2.1 centimeters.
Yep.
Yeah.
Therefore, the width of the central maximum is because by finding the y of this location, that's only half the width of the central maximum, so I double that number. Yes?
When you were drawing the pattern, does the single slit have to be lined up with the peak?
Yeah, in principle the slit should be lined up with the peak. Yes? Sure. Yeah. You could have found the width as 0.024 meters. That'd be fine also. I'd be happy with that. Yeah. I erased that part, but the reason is that the functional form of the intensity pattern is a sinc function squared of 2 pi sine theta A over twice lambda. Or it's a sinc function squared of pi times sine times A sine theta over lambda. Okay, let me write that function on the board, and maybe I can make it clear this time. Everybody good with this? I'm going to erase it. Okay?
I guess it's also
What did you have to double?
look at the weight.
I don't know about that.
Found half the weight.
Got it.
This is the result we had from taking the Fourier transform, okay? It has zeros at 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, because since a sinc function is sine x over x, whenever the sine part is 0, then you get a 0, okay? So, when this equals 1, you get the first minimum. When this, and by this I mean that part, when this equals 2, you get the second minimum. When this equals 3, you get the third minimum. Okay? And so, when that equals 1, this is the condition. When that quantity equals 2, this is the condition, etc. And so that's how we got to 0. And we did it by taking the Fourier transform and opening. Okay? I can also show that Fourier transform if you guys want to see it. Remember, one of those two is on the exam.
Yeah, I still like that.
Yes, yes. Okay. a minute. Let's finish our way through here, and if the next problem is not diffraction, then that's what we'll do. Okay? So, what is the width of the central peak? 4.2 centimeters. What's the width of the other peaks? 2.1 centimeters. Okay, because the central peak is double wide. And if blue light were used, would the pattern be narrower or wider? Narrower. Because blue light is a shorter wavelength, and so the A sine theta would be a smaller number, meaning the angles are smaller. Okay? So long wavelength light and the pattern is spread out, short wavelength light and the pattern is compressed. Everybody follow? Does it seem reasonable? Yeah. I can't hear you. Oh, I didn't know the exact value. All I knew is that it's narrower than red light. Because I know that red light is the longest wavelength and blue light is the shortest wavelength. Narrower. Okay, are we good with this problem? Okay, let's see what the next problem has to show us. Okay? One day in the lab, you pluck a human hair. I guess it should say from your head, but it doesn't specify. And shine a laser upon it. The result is a diffraction pattern on the far wall. The figure below shows the apparatus not to scale. Laser, hair, 2 meters, and a pattern. Does everybody follow? Laser, hair, 2 meters, and a pattern. Now, what does the diffraction pattern of a hair look like?
Maybe a single slit.
Looks exactly like a single slit.
Yes.
Okay? The reason is that, and this is part of the mathematics of doing the Fourier transform, it doesn't matter whether the pattern of light is a certain pattern of openings or exactly the same pattern of blockages. So, 2 patterns. One is a pattern of openings, and then the other one is a pattern of blockages. The interference is the same. So, a single slit and a single hair make the same pattern. What if you took 2 hairs? What would you get? Double slit interference.
Would you need 2 lasers, shot
No.
both?
Well, all of these slits are very small distance between them.
No, I know, but the light.
Oh! Somebody here has a laser!
Oh.
You have to give me your laser now.
For science.
He's like found.
Oh, yeah,
We're like half dead. Like,
So, mine comes out easier than yours. That's another age fact. Okay, so I'm going to try to pick one of these up. Oh shit, it's Greg.
There's the lights off.
Yeah, every day.
Hold on. And now I'm having trouble with my near point. And I'm trying to drape the hair across the front of the laser beam. And turn off a few lights. I don't know what some of those things are. Am I missing it?
Absolutely.
Oh, there it is.
Oh yeah, you got it.
Okay, now there it is for posterity. It's twice as big in the middle. Now there's also the main spot, okay? The main spot is really bright, but you can see the pattern on both sides of it. It's twice as wide in the middle, and then it gets successively dimmer with the other ones inside. So now, in principle, I have said that I should be able to make 2 slit